Yeah. So thank you. So I'm Debmalya Chakraborty from IPHTCA Saclay, France. So first of all, I would like to thank the organizers for giving me this opportunity. And I also want to apologize that I have changed the title of the talk because I wanted to accommodate two things in this talk which might be thought of in one go. So I would be talking about two cases of competitions in cuprates. The first case would be this, which is the phase diagram of underdoped cuprates at high magnetic field, where we will see the competition between two order parameters, one which is superconductivity and the other which is charge order. In the second part of my talk, I would be talking about effect of impurities in cuprates, where we will see the competition is between two phenomena, one which is disorder and the other which is strong electronic correlations. So for the first part, I have been doing this work with Corentin Morris and Catherine Pepa, who are also from IPHT. So we are in the land of Amazon, and I will be talking about cuprates, which we all might believe that is an Amazon of phases. So we have antiferromatic phase at low hole doping. We have, if we further hole dope the system, we have a D-wave superconductivity under a dome. We also have charge order at higher temperature, which shows short-range nature. If we put high amount of magnetic field, we see long-range charge order. We also have this mysterious pseudogap phase at higher temperature, where the antinodal parts of the Brillouin zone are gapped out. So in the first part of this talk, I will be focusing on this part of the phase diagram and want to study what is the competition or connection between the superconducting order and the charge order, and try to see whether there is some relation between these two orders and the pseudogap phase, which is at high temperature. So the competition or the connection between the superconducting order and the charge order is already evident in many experiments at zero or low fields. If we look at the superconducting transition temperature as a function of doping, we can see that this Tc has a plateau in exactly the same doping region where you see the charge intensity is maximum. If we look at the X-ray scattering intensity for the charge order itself, we can see that it shows a clear peak at T equal to Tc. If we see that there is a suppression in that intensity, and this suppression in the intensity reduces if we increase the magnetic field in the sample. For high field, there is no peak at Tc. This competition is also evident if we look at STM measurements. If we put some small amount of magnetic field, there would be vortices in the sample, and inside the vortex core, the superconducting order parameter would be depleted. Once superconducting order parameter is depleted, you can see that there would be charge order or charge modulation seen inside the vortex core. And very recently, it was seen in Raman measurements of Professor Alan Sakuto's group. What they could decipher is the energy scale associated with the charge order. And remarkably, what was seen is that this energy scale associated with the charge order is very close to the superconducting gap or the energy scale associated with it. The second remarkable feature is that all the three energy scales, superconducting energy scale, charge order energy scale, and also the pseudogap energy scale, they all behave similarly with doping in the whole doping region from 10% to 16%. So this competition is much more prominent if we put high amount of magnetic field. So this is a magnetic field temperature phase diagram, which I have taken from ultrasound velocity measurements of David Levov's group. So what they did was that at low field, you can see that you have a vortex solid or a vortex liquid. You have superconductivity in the sample. But if you crank up the magnetic field, you will see that there is an onset field above which superconductivity gives way to charge order. Interestingly, if you look at this onset field, this is quite flat with temperature. That means it does not depend on temperature up to a very significant amount of temperature. Second feature, what we can see is that at low temperature, there is a coexistence phase between superconductivity and charge order. There is a third very interesting feature is that if you look at the high field charge order transition temperature, TCO, is very close to the zero field superconducting TC. So this was also seen in NMR measurements. To be very specific, they looked at the TCO as a function of doping, and at 12%, they saw that this TCO is equal to TC, exactly. So in this first part of the talk, I will be focusing on all these features of the BT phase diagram of underdoped cuprates. And to be very specific, I will be focusing on the competition between superconductivity and charge order, and try to see whether we can get the features that were seen in the experiments. Or do we need an enhanced symmetry or intimate connection between the two orders, and whether we can associate pseudogap with it. So let me come to the competition only. So in order to understand the competition between two orders, we have started using the Landau-Ginzburg theory, where what we do is that we put a free energy like this, where we have a superconducting component, we have a charge order component, we have a coupling between the two. The superconducting and the charge order component both has a 5-4 form of the free energy. I will call the coefficient of the squared terms to be the mass of each field. So this would be the mass of superconductivity, this is the mass of the charge order. And we introduce a coupling between the two fields like this, and we take it to be positive because they don't like each other, they compete with each other. If we put magnetic field, what happens is that close to the upper critical field, we can treat the problem as an effective homogeneous theory, but with the superconducting mass being renormalized by magnetic field. So the superconducting mass will behave like linear in magnetic field close to the upper critical point, upper critical field. With this parameterization, let's plot the phase diagram in BT plane. So if we look at the BT phase diagram, magnetic field temperature phase diagram, for not strong coupling, that means if the two fields are not strongly compelling with each other. So for weak enough coupling, what we can see is that we will have superconductivity at low field, we will have charge order at high field, but we will also have a significant region in the phase diagram where we will see that there is a coexistence phase. If we look at it carefully, even at b equal to 0, we can have a coexistence phase. But in experiments, what we saw is that we need an onset field to get the charge order. So let's increase the coupling between the two fields. If we increase the coupling between the two fields, there reaches a critical value where the repulsion energy between the two becomes equal to the value of the individual energies of charge order and superconducting order. As a result, what happens if we go in this regime, there would be a first order transition from superconductivity at low field to charge order at high field, and this transition field is flat. So if we look at it carefully, is it really flat that we obtained in experiments? To understand that, I go back to the parameterization of the both masses. What we have done while plotting this, we have taken the coefficient of the temperature dependence of each of these masses to be equal. So let's see if we change it slightly. If we change it slightly, what happens? You can see that this line can be like this, it can be like this, it can be anything. So to cut the story short, we need extreme fine-tuning of parameters within a Landau-Ginzburg theory to get this flatness in the onset field. So we are not happy. So let's see whether we can improve with an enhanced symmetry picture. So if we have an enhanced symmetry between the two orders, to understand this enhanced symmetry, let me go back to the Landau-Ginzburg free energy. So if we take the two masses to be equal, and set that all the parameters such that the two energies are exactly same. Then plot the free energy in superconducting charge order plane. If we plot it, we will see that it shows a Mexican hat-like potential with equal energy contours being plotted here. So if we go on one equal energy contour, we can have different values of phi and psi, but the free energy will remain same. So as a result, we have an enhanced symmetry from a lower symmetry group, which was just superconductivity and charge order. Similar enhanced symmetry was studied by Efetov and Catherine 5 years back. So what they found is that there is an SU2 symmetry between D-wave charge order and D-wave superconducting order in underdoped cuprates. And the fluctuation between these two orders gives rise to the pseudogap phase at higher temperature. Within this picture, you can actually write a composite order parameter. Composite because it comprises of both the orders, the charge order in the diagonal channel and the superconducting order in the off-diagonal channel. So initially we had two U1 fields. Now we have a larger field which is SU2. So this matrix is a SU2 matrix. Because it's a SU2 matrix, we will have a constraint on the two fields. So what happens, because of this nature of the matrix, phi square plus psi square will be a constant in the right-hand side. So if this constant is fixed, I can show you that this will be, it's easily seen that this is very strong competition between the two orders. If superconductivity is high, then the charge order has to be low because it has to have a right-hand side which is constant. If the superconductivity is low, then the charge order will be high because the right-hand side is same. So there is a very strong competition between the two. We can represent this constraint by a pseudo-spin which lies in a four-dimensional space where we have a superconducting easy plane and a charge order easy plane, and this pseudo-spin can move around throughout this sphere, this four-dimensional hypersphere. And this does not need any energy to move from one plane to the other because we have these equally energy contours. So what happens if we actually break the symmetry? If we make the masses different, but not so much such that we break the symmetry absolutely, so we make the masses different, but they are very close to each other. So we have an approximate symmetry, but by doing this, what we have done, we have introduced an energy cost for this pseudo-spin to go from superconducting plane to the charge order plane, and this energy cost is given by the difference of the two masses. So in all what we have done, we have introduced two energy scale in the problem. One which is this right-hand side of the constraint, which is the SU2 energy scale, which will govern the high energy phases, the pseudogap phase. And we also have this low energy scale, this difference is small, which will decide the low temperature phases of the problem, which would be either superconductivity or charge order. In order to study the fluctuations of this pseudo-spin, we started looking at the nonlinear sigma model, where we have this term which is just the difference of the two masses, the anisotropy between the two fields. We have this term which is the gradient of the fields, which will take care of the fluctuations in the problem. So we started doing a renormalization group treatment of this free energy in two spatial dimensions and try to see what happens to the phase diagram. If you look at the phase diagram, it looks like this, where we will see that there is a superconducting to charge order transition. And in order to understand it, let me go to one line, t equal to 0 line. So let's see what happens. If we are at low field, if we look at the free energy in the superconducting direction and the charge order direction, there is a minima in the superconducting direction which is at a lower energy than the minima in the charge order direction. As a result, the system is in the superconducting phase and the pseudo-spin is in this plane. Now if we increase the field further, what I told you earlier, that the superconducting mass is being renormalized by field. As we increase the field, superconducting mass goes higher. So as a result, the superconducting mass goes higher and it becomes equal to the charge order mass. So the two free energies, the minimas come at the same place, and there is no difference in the energy, and we recover the exact SU2 symmetry exactly at this point. If we increase the field further, as I said, it will go further higher, but then the charge order minima will be lower. As a result, the system goes from superconductivity to charge order through a direct transition, and the pseudo-spin, which was lying in one plane, now will flop to the other plane, and there is a pseudo-spin flop transition. If you look at the functional form of, before going there, I was talking just about t equal to 0 line. So let's see what happens if we increase the temperature. Yeah. This is first order. Yeah. So if we are at lower fields, lower than this B0, we are in superconducting phase. Let's increase the temperature. Increasing temperature will increase the thermal fluctuations in the system, as she was talking about. So the pseudo-spin, which was lying in one direction, now will start fluctuating, and there would be one point where within this renormalization group treatment, this anisotropy gets renormalized in this RG process, and they become exactly equal at this line. So what happens is that if you increase the temperature further, there is no anisotropy. As a result, the system hesitates between charge order and the superconducting order, and the superconducting order or charge order at high field will go to a pseudogap phase, which will be a disordered mixture of charge order and superconducting order with no long-range coherence. So if you look at the functional form of this BCO, you can see that there is an exponential -1/t dependence. That means it's exponentially flat. And this flatness is not dependent on any parameters, so it's not specific to any fine-tuning of the parameters in the system. So we can reach this flatness, and the extent of flatness is controlled by this parameter, which is the stiffness associated with this symmetry. So we are happy, we are partially happy because we have obtained the flatness, but we have not got the coexistence, because I was showing you that in experiments, we need a coexistence phase at low temperature. In order to achieve the coexistence, we have to break a higher order symmetry. So I showed you the BT phase diagram for this part only, which was this, where there is no coexistence. If we need a coexistence, we need to break a higher order. This is just mass being different. Now you have to make higher order corrections. And by this symmetry breaking, we can get the coexistence phase here. So we are very happy because we got the flatness that was there in experiments. We got the coexistence phase. And because of this symmetry between the two energy scales, what we also see is that the zero field transition temperature for superconductivity, Tc, is very close to the high field transition temperature for the charge order. So I said earlier that I will be focusing on this part of the phase diagram. Now let's go in this direction, close to the so-called pseudogap quantum critical point. What happens if we plot the phase diagram in BT plane, we see that the flatness is gone. So it's no longer flat, and the onset field is now dependent on temperature quadratically. There are some very recent experiments, ultrasound velocity measurements, where they measured the BT phase diagram in 12.2% at 2, which is here. They saw that the flatness is there. But if you go from here to 13.4% doping, then you will see that the onset field now depends on temperature. We have not fitted it with this data, but you can clearly see that there is a very good temperature dependence on the onset field, and it's no longer flat. So till now, I have not talked about any vortex-induced inhomogeneity. So if I look inside the vortex, so as I said earlier, that the superconducting order parameter will be suppressed inside the vortex. At the center, it would be 0. Now remember, we have a constraint on the 2. So as a result, one order parameter was 0, so we actually enhanced the other order parameter, which is the charge order, because of this constraint, which we also saw in STM measurements. Interestingly, there would be a region around the center, which is called the vortex halo, where you can get a coexistence phase of charge order and superconducting order. And this was also seen recently in STM measurements. If we increase the field, these halos will condense, and in this portion of the phase diagram, they will form, we can say that there is a possibility they will form a PDW phase with the same lattice spacing modulations as the charge order phase. There are also possibilities that it can be a supersolid phase, but let me make it clear that this PDW phase is a 4 lattice spacing modulation, same as the charge order, and not the PDW phase recently proposed by Patrick Lee and others in this paper, which has 8 lattice spacing modulations. So I would first now give the conclusion of this part. So what I tried to argue is that even from looking at the BT phase diagram, we can have some evidences or indications that there is an enhanced symmetry or SU2 symmetry between the superconducting order and the charge order. So at this point, I would like to pause and take some questions if you have on this part. Yeah, so there are no evidences of the first order nature. So there was no hysteresis or some, so it was not seen that it could not be a first order, it was well established. Wait, so I have not shown how do we get it. So it's, if you solve the Landau-Ginzburg equation, I think I have a slide on that. So what happens close to the upper critical field, since you have many, so since I have time, I can show it. Maybe, yes. Okay, I will do it later, because I would be revealing all the next slides then. I have a slide on that. So let me come to it at the end. Yeah, so it will be linear in B, because if you solve the Landau-Ginzburg equation, you will see that the eigenvalues are linear in B. Yeah. Okay. So if you have any more questions, I will come to your question later. So now let me go to the second part of the talk, where I will be talking about effect of impurities in cuprates. I did this work when I was in India doing my PhD with Professor Amit Ghoshal and Rajdeep Sen Sharma, who was our collaborator from India. So what I would show you that superconductivity also behaves very weirdly, and it is immune to impurities. So I'm revealing the end point at the first slide, that it will be immune initially to weaker impurities, but it will suffer a sudden death if you go to stronger impurities. So we know that cuprates are strongly correlated materials, because at least at half filling, we know that it's a Mott insulator. So strong correlation is important in these materials, at least at half filling for sure. Also, we know that disorder is ubiquitous in cuprates. For example, if you dope the sample, you introduce weak out-of-plane disorders, which are considered mostly to be weak. You can also substitute the copper ion by some other transition metal ion in the copper oxide plane. That will be called as substituents, which will also introduce impurities. They can be weak or strong depending on which transition metal ion you are using. So what is the experimental status on the impurity effect? So if you look at, again, STM, so look at the gap map in the sample, we can see that this is red is low, so there would be some places which are low in gap, there would be some places which are high in gap. So the gap map shows that there are nanoscale inhomogeneities in the sample, and that persists for all dopings. If you plot the distribution of this gap, you will see that it's a Gaussian distribution like this. Interestingly, if you want to look at the density of state of different regions, if you look at the density of state at the red region, which is this curve, if you look at the density of state, say, for the black region, which will be this curve, they have different gaps, because as you can see that they have different gaps, but as a result, they will have different positions for the coherence peak. But interestingly, what happens is that at low energy, the density of state is quite robust to impurities. You take the density of state from different regions of the sample which has different dopings, but the low energy density of state is robust. If you look at other measurements like superfluid density or transition temperature of the superconductor only, we can see that if we increase the substituents in the sample, that means suppose we have weaker impurities like nickel or iron, we replace copper by nickel or iron, the reduction in Tc as a function of the concentration of those impurities is not that strong. But if we replace it by a strong impurity, which is zinc, then you can see that it suffers a sudden death. With very small concentration of zinc, you can kill superconductivity. So experimentally, we can see some features that it would be robust to weaker impurities, and so strong impurities will kill superconductivity. In order to understand this interplay between strong correlation and disorder, let me show you this cartoon. What happens if you have an upspin at ith site and a downspin at jth site? If you want this spin to hop from this to this, it will form a double occupancy. If the repulsion between the electrons is very strong, they would not like to form this state because it would be a very high energy state. So with strong correlation, it's not allowed. But if you don't have the strong repulsion between the electrons, it's fine. It's a happy hopping. Now let's introduce disorder in this problem. So for here, let me show you schematically. Suppose you have an attractive potential on the jth side. So this electron will now want to hop here. this is a happy hopping if you don't have strong correlation, because you are going from a higher potential to a lower potential. So this is a happier hopping, but with strong correlation, it's anyway blocked because you don't want double occupancies. So what it shows that the effect of strong correlation become much more prominent if you have disorder in the sample. In order to physically understand what's happening, there are two phenomena occurring. One, disorder, which wants to make the system inhomogeneous with charge puddles everywhere. But if you have strong repulsion between the electrons, they would not like charge to accumulate. So they would smoothen out the charge accumulation and try to smear out the charge inhomogeneity. As a result, they compete with each other very strongly. So we started with a repulsive Hubbard model. As many of you know that for very large U very, very greater than T, you can do a Schrieffer transformation, which takes care of the fact that you remove all double occupancies and virtual processes. You can go up, you can land up with a TJ model, and then we introduce disorder in this problem. After deriving this TJ model, we introduce disorder like this, which is just on-site chemical potential. And we will take parameters which are relevant for cuprates, and to be very clear that I will be working at this homogeneous doping. That means the average doping of the sample would be around optimal doping, and I will not consider any competing orders now. So now I will forget about charge order or antiferromagneticism, any other. So what would be my focus would be to see what is the effect of impurities on superconductivity alone. We have used many models of disorder, but I will focus in this talk only on the box disorder, where we put random impurities on every site, taken from a distribution which is like this. The width of this box will determine the strength of the impurity. Filling? It's 0.2. Doping is 0.2, so it's 0.8. Density is 0.8, which would be around here, optimal one. That is the average doping. So how to solve it? We wanted to take care of the inhomogeneities in the sample. So we did a Bogoliubov-Digens theory in real space, because we have disorder, which I will call inhomogeneous mean field theory. And to incorporate the strong correlation, we have done a Gutzwiller approximation, and I will call this method with both Gutzwiller approximation and BDG theory in real space to be GIMT, which is Gutzwiller inhomogeneous mean field theory. So I would use these acronyms later. Let me give a short introduction to what we are doing in a Gutzwiller approximation. What we are doing is that since the double occupancies are not likely in the sample because they don't like each other, its repulsion is very strong, we take these states out of the Hilbert space. As a result, the parameters in the problem, like hopping parameter or the J parameter, the super exchange parameter, gets renormalized by factors which are called Gutzwiller factors. In a simple-minded approach, you can calculate these Gutzwiller factors using a phase space counting arguments, because you have taken some states out of the sample or of the Hilbert space. So what happens, you can calculate this Gutzwiller factor. I will show you for one. Let's look at the kinetic energy term. What happens, you have one Gutzwiller factor in front of the normal kinetic energy term. This Gutzwiller factor happens to be given like this, which is 2 delta plus 1 plus by 1 plus delta, and delta is the doping in the sample. So let's look what is being done here. If we are at half filling, that means the density of electron is 1, the doping is 0, so this factor is 0. That means you have no hopping in the sample. You mimic the Mott insulator nature. If you go to the other limit, which is the limit where you have very less number of electrons, then the doping will go 10 to 1. As a result, this factor, you can see that for delta equal to 1, this is 1. As a result, you have no strong effect of strong correlation. And it's obvious, because if you have very less electrons, they are far away from each other, they don't talk to each other, then why would you even expect an effect of strong correlation? But with disorder, these factors are no longer dependent on the average doping. They will be dependent on the local doping, and they are different at different parts of the sample. So we have to do it self-consistently. These factors are now have to be calculated self-consistently. So we looked at the physical observables, like off-diagonal long-range order or superfluid density. What happens as we introduce disorder in the sample? So what is off-diagonal long-range order? It's like long-range correlation. So you have a Cooper pair in a bond, you annihilate it, you create it far away. What is the probability of this process? So this is given here. So if you look at the off-diagonal long-range order, we have normalized it by the homogeneous value. In IMT, with no strong correlation, if you introduce disorder, this value goes down, and superconductivity is killed at around 2.5 T. Remarkably, if you introduce strong correlation in GIMT, you will see that it's quite robust to disorder. The value falls hardly 5 to 10%. It's so robust that you can also see in superfluid density that it behaves very similarly. That IMT falls down, but GIMT doesn't. So what happens in the density of state? Let's look at it. So if we look at a normal D-wave superconductor, it's like this V-shaped density of state. If we introduce disorder with no strong correlation in the lower panel, you will see that as you increase disorder strength, it will be flat with no coherence peak, no superconductivity, and no gap. The mid-gap states would be completely filled up. If you include strong correlation, you can see even for this flat density of state without strong correlation, if you include that in GIMT, it would be robust at low energies. It is exactly very similar to what we saw in experiments, that the low energy density of state would be robust to impurities. Now, if we want to understand what happens to the inhomogeneities themselves, so in our problem, we have two primary order parameters: the density or doping, local doping, and superconducting order parameter. So if you look at the distribution, as I told you, we have taken a box distribution for the disorder, so we expect the density to behave similarly. So in IMT, we will have more or less like a box distribution, and if you increase the width, this also increases. But you can see in the same scale, if you include strong correlation, it shrinks. So if you include strong correlation, the inhomogeneity in density gets reduced significantly. As a result, if you look at the gap distribution, you will see in GIMT, it shows for homogeneous, it should be a delta function. But once you increase disorder, it widens, it becomes a Gaussian. More or less for high disorder, it still remains Gaussian. The width increases, but the mean value remains at the same place. This was very similar to what was seen in experiments like this, a Gaussian nature in the distribution of the gap value. Now, in order to understand what happens locally, let me show you the right-hand panel first. So what is this? This is a 30 cross 30 lattice. We plot the superconducting order parameter itself. For low disorder, it should be more or less same everywhere. If you increase the disorder, what happens, you form superconducting puddles if you don't have strong correlation. Why do they form? You can look at this schematic. If you have a high hill, electron would not be there, so the density would be 0. So, even because density is 0, the order parameter would be 0. If you have a very deep valley, the density would be 2. There would be double occupancies, no superconductivity. Only in regions where you have very average density, that means close to average density, you will have particle-hole mixing and you will have superconductivity. So there would be superconducting regions separated by non-superconducting regions like this, which will be a distribution like this, where you have all values, most of the values at 0, but with a long tail. Yeah. 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 So yeah, I should have been careful. I'm actually talking about no Gutzwiller approximation now. So this IMT, I should have made it clear. So IMT is no Gutzwiller approximation. GIMT is with Gutzwiller approximation. So if you do not have any Gutzwiller approximation, you will then form double occupancies. This is the explanation for the right-hand side of formation of superconducting islands. But interestingly, what will happen if you include strong correlation, as you were saying, you will not have these double occupancies. And then the nanoscale inhomogeneities behave very similarly. They will never form superconducting islands. Yeah. So we are doing BDG on this. So yeah, we have this Hamiltonian with disorder. We replace this tilde with the projection operators by these Gutzwiller factors. And for IMT, I will have these Gutzwiller factors to be 1 because they are not dependent on density. For GIMT, which is with strong correlation, then I will have these Gutzwiller factors which will take care of the strong correlation. No, because I have already made this. I have already made a threefold transformation and written it a TJ model. I am not working with the Hubbard model, because since U is very large, of the order of 12T in cuprates, so yeah, formalism. Yeah. No. So what happens if you have, so we are actually taking them out from the problem, because when we do Gutzwiller approximation, you remove all double occupancy from the system. We don't allow any partial, because 12T is like, so if I show you the band, you will see that there would be two bands. This would be 12T. So this band is just single occupancy band. This is the double occupancy band. So they don't talk to each other. We are just working here. And since this is a very large energy scale, they will be out of the problem. So we want a low energy effective problem where we work here only. Yeah. So, but I will have times for questions. So, okay. So as he was pointing out, you will have no double occupancies, and in GIMT, you will see that the superconducting order parameter shows just nanoscale inhomogeneities with no superconducting island formation. Fine. Let's look what is actually going on. Since we are doing a mean field theory, we can always write the whole Hamiltonian into a single particle Hamiltonian like this, where we have the hopping with an effective hopping parameter. We have a density with an effective on-site potential and the pairing terms. So what is happening is that if you have a very high disorder potential, Baire disorder, to be very high at I, the density would be very low because electrons don't want to sit on a high hill. Since the density is low, this Gutzwiller factor will then increase. As a result, the T effective hopping into that site will increase. And the density would no longer be as low as it was in the Baire potential. And if you think in terms of a renormalized effective potential, this renormalized potential will be not as high as it was given. So there are three processes how the system reduces the inhomogeneity. First, it screens the disorder because of the Coulomb repulsion. It introduces a bond disorder because earlier T was just a constant everywhere. Now T depends locally on the local disorder potential. And also, interestingly, these two go anti-correlated with each other. That means the places where T would be high, V would be low, so they compete with each other, making the system far more homogeneous. So all is fine. We have immunity at weak to moderate disorder. Now, what happens if we increase the disorder strength? Let us increase it beyond the bandwidth, but not beyond U. So U is still the largest energy scale in the problem. We increase the disorder scale much greater than T. Should we expect the superconductivity to survive and be robust? To understand that, we should think about this transformation again. What we did earlier was that we took Hubbard model, did a threefold transformation, and in threefold transformation, as I was showing earlier, that you have these virtual processes which are high energy, so you actually come back, which results into these spin flip processes, which gives you J term. So you have two effectively two subbands which are clearly separated from each other because you have a difference of U, and we work in the low energy subband and no mixing between the two. This is just the threefold transformation. So we get a TJ model. Then we added disorder. But is it right if you have strong disorder? No. If we make V much larger than T, but still U is the largest energy scale, so there would be no double occupancy still, but there would be some additional processes, so we have to start with a model which is Hubbard model plus disorder, then do a threefold transformation, and then obtain a model which is different for different, it will have different T's on different bonds. Why? Because you will have these processes. Even if this site is empty, you can see if this site has a high disorder potential, this electron will go there, but since it's a high energy, it will not like it. It will come back. It's a virtual process. It will stay at the same place. So there will be virtual processes that you have to take out of the system. Effectively, what we'll do, we will introduce t square over v processes and cut the direct hopping. That means if there is a hopping from electron at this site to this site, it would not like to go there. We will cut the hopping. That means there is no hopping between these two sites. If you do this, then you will see that up to a disorder strength which is comparable to the bandwidth, you will see superconductivity is robust to disorder. Then if you increase it further, it suffers a sudden death and it goes to 0 at around 6 to 7 T, which is still much lesser than 12 T. If you look at the density of state, it was quite robust for weaker disorder, but if you make it very high, above the bandwidth, you will see that there would be states, in-gap states forming here. And the coherence peak also gets down. To understand what is actually going on, we look at the formation of the superconducting islands if you have very strong disorder. What will happen is that you will form superconducting islands like this, where these blue regions are high superconducting. So in these regions, the superconducting order parameter is high, but they are in a matrix which is non-superconducting, this green and red region. Since you might say that this is very similar to what we saw in IMT, but it is not. Because what is happening now is that you have two kinds of sites in this non-superconducting matrix. So the system can be broken into three kinds of sites. The blue sites, which are the superconducting sites, you have regions or islands of superconductivity. They would be separated by regions which are non-superconducting, which will comprise of two things. One, which is these red dots, which would be the Mott sites, where you will have Mott insulator. And even the surrounding of the Mott insulator would be Anderson insulator and not a Mott insulator, but still they will kill superconductivity. So there would be this whole insulating patch comprising of two kinds of insulator, Mott and Anderson. Earlier we only had Anderson insulators. And how to distinguish them? You can look at the density of state. If you look at the Mott sites, they will really show a clear Mott gap. If you are in the other site, which is the neighbors to the Motts, which are the Anderson insulators, they will have no features at the gap scale, and they would have a very sharp gap at low energies. So you can clearly distinguish between these two sites. So I would like to conclude by saying what was happening. This is the second conclusion for the second part. We still have competition. So for weak to moderate disorder, they compete with each other. Disorder and strong correlation compete strongly to make the system robust to impurities. Superconductivity is then robust to impurity. If you increase the disorder strength such that you are above the bandwidth, then they join hands. And then they join hands by forming Mott sites and Anderson insulators, and then killing superconductivity jointly. So, thank you.